So let's discuss about the fatigue analysis, spectral fatigue, third lecture. Fatigue is just not a member, it's not just numbers. It's a silent conversation between the stress and time. For example, if this some particular joint is getting subjected to a lot of stress and how much time it's going to sustain, that's the additional relationship between these two. And relay is the principle that we are going to use it for this randomness, and root mean square of particular signal is nothing but its strength, and spectral moments show the rhythm, and gamma shows the harmony. We will discuss all these things. Okay, so we will have a group discussion. Ravi is talking about here's a real stress record from the platform joint. So he's getting a stress record from the platform joint. It's 5 minutes long. For example, this is my jacket structure. Okay, this particular joint I'm taking, and this particular joint I have this cord, and then this brace, this one brace. Even at this brace also, at this top corner, if I take as a top corner, this particular joint, it's going to experience stress, because when the wave comes and goes, like it will, the stress also, as time goes up, the stress also it can vary, stress value also it can vary, like when there is no wave there is zero stress, and the stress can go up and down because the waves can come and go. Like this it will keep going for 25 years. 25 years this particular joint, at particular joints, this particular spot is going to experience the stress variations, stress cycles. So this is the stress cycle is going to act for 25 years or 30 years, whatever the lifetime it's going to experience. So we want to find out like how long it can sustain, right? So this time period, if you take 25 years, and this is a stress value for this particular joint and particular point. So this brace, if we equally distribute this joint as 8 points, it's going to experience a lot, right? So in this one we can see this particular time is stress history with respect to 25 years. It takes one cycle. For example, this is the one cycle, and next cycle is this one. Like this it can get n number of stress cycles. So we want to know how many stress cycles are happening in 25 years, right? Then we can come back and see that whether the stress cycles it can sustain for that many number of cycles or not, like how much damage is going to happen like that. So we can see the stress value. This is the stress, maybe here 1 MPa, 2 MPa, 3 MPa, 10 MPa, something like that. So if this is what is the average stress, that's a root mean square also we can take it. So but in this example we are going to see just 5 minutes. So the joint is going to subject with 5 minutes, wave is coming and going. Within that 5 minutes what's happening, like that we can see. So it looks like a heart monitor, up and down, up and down. Exactly, each full up and down is one stress cycle. So the first step is count how often it wiggles. So right, well, we will get that from the spectrum instead of counting by hand. Just now I'm counting it by hand. Instead of that we can go and use a spectrum. So see, this is the spectrum, you can see. So yes, sigma with respect to frequencies, how much stress power exists at each frequency. So here in that signal we can see how many frequencies are there. So for example, this is one frequency, and this is another frequency. This could be another frequency, this can be another frequency. Frequency means like how much time, inverse of time, right? So we can see a lot of frequencies. So one random signal, this is with respect to time, and this is with respect to, even if you see as a wave surface elevation. So this is the time record. From this time record you can get how many frequencies are there and what is its strength. We can get, this is using the fast Fourier transform, we can convert the time history to frequency domain. So we can see how many frequencies are coming and what is its strength, right? For example, this period is 10 seconds, means frequency will be 0.1. If this period is just 3 seconds, means frequency will be 0.3. So mostly we could see it will be following like this kind of distribution. We more often we get these uh, low frequency waves. That means low frequency means like more time, long time, and high frequency waves are quite low. This is how the ocean is. Ocean will be there. Ocean is just a mix of a lot of waves. Few waves are quite long and few waves are quite short, and it takes a lot of time to come. Few are quite frequently it's coming. So high frequency waves and low frequency waves, so it's a mix of a lot of waves. Okay, so from that we can convert any time history to frequency domain. The same with the stress history. Stress history also we can convert into stress spectrum. So this is the stress spectrum. Okay, this area under this stress spectrum gives how much is the energy. So for this particular frequency, what is the stress density, we can calculate it. Okay, this is why power. Why are we saying it power? Because the stress is stress squared is energy. The PST tells us where that energy lies, slow or fast waves. And what do m0 and m2 mean physically? m0 is the total energy, m2 is weighted toward fast motion. If you plug in the numbers, the spectrum say m0 is this much value, 400 MPa squared, and m2 is 1600 MPa squared. The m2 is the bigger because fast vehicles add weight. Now the average period, we can get the average period, square root of this. So m0 by m2, say example 0.25 seconds, average period between zero crossings. So what does it mean? Like it is crossing like this, right? It is crossing like this, and quickly something crosses, something takes little more. So we are just wanted to see the average crossings. Average crossings we can get from that spectrum using this formula. So it takes average is nothing but 0.25 seconds. It means like, meaning every quarter second stress crosses zero once. One cycle every half second. So that means about 2 cycles per second. It's nothing but 2 cycles per second. So in 1 hour, in 1 second 2 cycles means in 1 hour how many cycles? 1 second is 2 cycles. Then 1 hour means 3600, right? That means that is 0.5, but if you take the tz value is 0.25, so 0.5 means 1 in 4, right? So that means 3600 into 4 equal to 14,400 would come. So what is our typical stress level? So we can see the average stress level, that's a root mean square value, and that is coming around to be 20 MPa for example. So the structure vibrates around 20 MPa on average, sometimes more, sometimes less, right? It is an average value. So exactly think of it as an average energy of shaking. How do we describe which stress range happen most? So how do we describe which stress happens most? So that's where we come up with Rayleigh probability. The probability of Rayleigh probability, this is the formula. Why this shape? Because most cycles have small medium ranges, very big ones are rare. It rises, peaks near 2 sigma and then decays. It's nothing but, if you see this formula, it starts with 0 and it rises sharply to the peak, and then it goes like exponential decay. Why this exponential decay? This e power minus stress squared is coming, right? Exponential power. So this is the exponential curve, right? So it means like these are the stress values and this is the probability. So probability is dropping quite a lot exponentially for higher stress events. So that means higher stress events are not going to happen more often. Only the lower stress events are going to happen quite often. These are the lowest stress, these are the highest stress. Because why is that happening like that? Because most of the time you will be getting like small wave heights in the ocean, and larger wave heights are quite rare to happen, right? That's why this kind of shape is coming. Why do we choose the Rayleigh function? Means in the ocean we are going to see the small wave heights. So small wave heights cause smaller stresses events. So the small stress events are peaking, and then these high stress events are exponentially dropping off, and that's why this is mathematically pictured as a Rayleigh distribution function. All right, so what is this value? This value is the most probable, right? That the root mean square, double the root mean square. So let's start numbers. If sigma is 20 MPa and stress, so sigma, that root mean square is stress. So how much is the probability for 10 MPa? So we are going to get 0.009, that means 0.9 percentage. 20 MPa, 40 MPa, 60 MPa, if you plug it, you are going to get this kind of percentage of occurrence. So small ranges dominate, big ones fade fast. That's what is happening, right? Small ones dominate and big ones going to fade because of this exponential term. That's why there is exponential term of e power minus. E power minus some value is there, and here some power function and exponential function. If you see in the mathematics, there is a gamma function. Gamma function is nothing but it's a integral. It's going to relate this power function and exponential function. So gamma function is nothing but factorials. So that's the ocean, many small waves. So what's happening with this? Ocean means what? The ocean is nothing but many small waves and few big ones, and that's how it's getting reflected in this radial distribution. So how much life does each stress cause? So for steel we use, this is the SN curve. So cycles to failure is inversely proportional to the stress value. This is the experimental constant. Leave it that. This is stress value is inversely proportional to the number of cycles for failure. That means if the stress value is quite high, the number of cycles to failure is dropping a lot, right? So take this value and take m equal 4. So for 40 MPa, the cycles to survive is, for 40 MPa cycle to survive, a value is 10 power 12, and stress value is 40, and stress power m is, for m is nothing but in S and curve. This is the stress value and this number of cycles to failure. This is the slope. I'm just assuming a single slope, but and actually you are getting the dual slope. For these are the this portion is the low stress and this portion is the high stress. For where we have the high stress portion, the slope is very steep, and where we have the low stress portion, slope is little gentle. That means m equal to 3 here m equal to 5. So high stresses are going to cause quick damage, but even though these are rare to occur, but once it's occurring, you are getting a number of cycles is very less. So when these stress values are quite high, the number of cycles to failure is dropping a lot. So once you plug all these values, you are going to get, for this particular stress, you are going to get the number of cycles to failure is this value, 3.9 in 10 power 5. Then you will get, that's life. Damage for a small group of ranges. So we can get small group of ranges. This is the probability and stress values. That looks like how many cycles occur, how damaging each is. How many cycles is going to occur, each cycle how is it damaging. To get a total damage, we add all ranges, we add up all. But the integral looks impossible. That's where the gamma function saves us. This integral, the gamma function helps us. Gamma function, if you see this, if you change variables cleverly, the integral becomes the pattern x power g power minus 1 e power x. It's nothing whose value is gamma g. So it's like a magical color over the shapes, right? Exactly, the answer is that gamma 1 plus m by 2. We can use it gamma function. So let's plug the numbers. Total number of cycles we know. This is the in 1 hour, because we know mean zero crossing period is just 0.25 seconds. So in 1 hour we are going to get this many cycles, and this is the root mean square of stress value, this m and a. Once you plug in all these values, like a 2 power sigma square m by 2 is 6.4, and gamma into 1 plus 4 divided by 2 is gamma 3 is 2 factorials 2, and d power, so we can get the damage of this much. So that means like after 1 hour about 1.58 percentage of total life. Damage is 1.8 percentage of total life. That means that this part would last about 1 divided by 0.01 is, that means 55 hours under constant conditions. So this stress cycle with a range, I think it can last up to 55 hours under constant conditions. That's not so. Real sea states must vary a lot. So what if the RMS rises just by 10%? So damage is proportional to the stress value per m. So 1.1 per 4. That means damage is almost, it's dropping to 38 hours. That means 30% are shorter. So if the stress soars up by just 10%, damage is also going up. That means life drops by 30%. Stress is increasing by just 10%, but life is decreasing a lot by 30%. So a small stress changes means big life changes. That's why ships slow down in storms to save structural life. Why do you assume Rayleigh at all? This is a good question. Like, why do you assume Rayleigh at all? Because for narrow band Gaussian signals, it is statistically correct. If the spectrum widens, we would use corrections or direct cycle counting. What if our m value changes? If material is brittle, m increases, then damage rises much faster. If m is increasing, means this is the m3, this is the m4, this is the m5, this is m7, this is m9, like that. If the m is increasing, for the stress values, even small stress values, so you are for example, this particular stress value, m is flat, little bit flat, number of cycles to failure is quite high. If for this m is less, for the same stress, your number of cycles failure is reducing a lot, right? That's why this m plays a lot. This m depends on this material behavior, right? M is the slope of this SN curve, that depends on the experimental value, but this m value, it depends on the material, right? If m is increasing a lot, that means slope is increasing a lot, then your damage also rises much faster with stress. Why does gamma appear 1 plus m by 2 and not m? Because when we integrate sigma or m exponential, sigma per m and exponential per m, the power of sigma r squared produces m by 2 in the exponent. Why is the total probability 1? If you integrate everything, it will become 1. Every possible stress range must occur with some chance. So all chances added equal certainty. Why do we use sigma squared instead of sigma? Because energy, thus we take latest to the square of stress. Why exponential? It naturally describes decay. Rare big stresses fall off fast. So this formula hidden the entire story. How often stresses come, and how big they are, and how the material reacts, and how it slowly dies. Fatigue statistics, physics, empathy for all metal at once. Metal could speak, it would whisper Rayleigh's curve and hum root mean square energy. Gamma function would be its memory for all cycles it survived. By understanding these, we can design smarter. Alright, let's go few more. Here's a 5-minute stress record from our component. The wave form jumps up and down like oceans. This is 5 minutes. Say this is the stress value. The stress is going like this. Assume for the 5 minutes that particular joint I am seeing stress is going up and down, suddenly some quite high waves. This is the stress history for the 5 minutes. Imagine, why do stress lines wiggle like this? Because the component feels loads that vary with time. Waves, wind, ship motion, each up and down is one stress cycle, right? Can we just count them to find the cycles? We can count, but for long data or random waves, counting cycles directly is tedious and error prone. We will use the spectral methods. Spectral methods is like missing notes. Exactly, each frequency in the stress signal is like a note. Some notes strong, high stress energy, and some are weak. The spectral moment summarize. The stress spectrum is this value. It's a power spectral density. It tells us how much energy is at each frequency. At each frequency, how much energy is there. High energy at frequency, big wiggles at that frequency. What about M0 and M2? That's a total variance, how wide the stress swings are weighted frequency squared. Tells about rabbit fluctuations. Can you give numbers? Example, this we have seen. If you put these two values, you're getting 0.5 square root of m0 by m2. So stress crosses 0 every 0.5 seconds. That means 2 cycles per second, right? Yeah. So in 1 hour we are getting 7200 cycles. So root mean square tells us the typical stress magnitude. So we can see the typical stress values here. In this also, here you can see, say this is 1 MPa, 2 MPa, 3 MPa, 4 MPa, 5 MPa, 6 MPa, 7 MPa, like that. We can get this average value, right? Typical value. That the root mean square value, we can get it. That's from the spectral parameter values. So usually this stress is around 20 MPa, sometimes or more, sometimes less. If sigma doubles, fatigue life, fatigue damage increases. Yes, if this doubles, fatigue damage increases. So the damage depends on stress value. So even small changes to this sigma can have big effects. Even small stress to this, it will have big impacts. Exactly. If this in the 5 minutes, if you have seen a lot of stress cycles, or you can see small stress cycles, so it's all depends on the stress value, time and stress. So if the stress is a lot and fatigue damage is quite high, we use Rayleigh distribution to find probabilities of stress range. Probability of that particular stress range. Why this formula? For narrow band Gaussian signal, the stress ranges follow this pattern. Small ranges are common, very large ones are rare. Let's try an example with this is the root mean square value 20 MPa, sigma stress of 10. So this is like this, imagine. So 10 MPa is just 9%, and 20 MPa 21, then 40 is 24, and 60 it's 14. So if the small to medium stresses dominate, big cycles are rare. The material response relation curve n equal to a per sigma. A is the material constant, m is the slope, depends on the material. For steel, usually we can take as 4. Alright, A equal to 12 for example, right? So example, the stress value is 40 MPa. If you are getting a stress of 40 MPa, a number of cycles to failure is, this is the stress range. So each cycle causes this much of life, 1 by n. So damage from all ranges are in integral form. Why integrate? Because all damages come from all possible ranges, weighted by how often they occur. So we can use this gamma function. We can reduce this integral to gamma function. Why gamma? Gamma is a special function, like a factorial for real numbers. Gamma is like a factorial for real numbers. So it tells us the effect of all stress cycles in one step. No need to integrate manually. So if you plug in all these values, number of cycles per hour, sigma, all these values, and you can get a damage of this one. That means 1.8% per hour. 1 hour we are getting 1.8% damage. So total life will be 1 divided by 55 hours. In 55 hours, 1 hour 1.8%. So 55 into 1.8 is how much? 55 into 1.8, that's becoming 100%. That means it's failing, right? So in 1 hour, how many percentage is happening? 1.8. 1 hour, suppose if it is 2%, it can have only 50 hours only it can withstand, right? So this percentage, how we are getting it? 1.8%. That comes from this value, damage value. Damage value, how we are getting? This is the number of cycles per hour. In 1 hour, how many cycles happening? And then this is the allowable values for that stress value of 20 MPa, right? 20 MPa, A into, Here you can see A and stress power M, right? Yeah, you can say stress power M. Here value is also 2 into sigma square, sigma naught squared. So sigma r is approximately 2 times sigma naught, sigma r 2 times sigma naught square, right? That's fine. Yeah, you can get 2 times sigma naught. Sigma naught is sigma naught square, right? So if RMS increases by 10%, damage is happening a lot. 1.4, that means 38 hours on it's coming. Why assume relay? Why RMS square values? RMS squared in probability. Why gamma appears? What if the spectrum is wideband? Relay works only for narrow band. RMS square represents energy related to fatigue. Gamma comes from integral. This stress power m into exponential into stress exponential power. So wideband need corrections or rainflow counting. Can we visualize which cycles cause most damage? How does zero crossing relate to real peaks? Damage concentrates in rare large cycles even if small cycles are frequent. Zero crossing gives frequency info, not amplitude details. Approximate, right? Think of metal like a sponge. Each stress wiggles, squeeze it slightly, and the small bubbles do a little damage. Rare big one squeezes hurt most, right? So if fatigue is like counting small dents and rare cracks, spectral approach helps us do it statistically without recording millions of cycles. So by knowing the sigma value from the spectrum and material constants, we can estimate the life even before testing full hours. So what are we going to get? Measure the stress, compute the spectral moments, RMS and average period. So we need to get the average period and RMS value, RMS stress, these two. Then assume the probability of ranges. Then use SN curve for damage per cycle, integrate all over, use gamma function, simplify integral, check sensitivity, question everything. Alright team, we have the steel beam that has been exposed to random loading. We are going to calculate the fatigue damage using spectral approach. We are going to do these real numbers, right? So exactly. First let's set up the basic parameters. The RMS value is sigma naught 20 MPa, material constant, slope. We are looking at a time period of 1 hour, say. We have the following stress ranges. These are the stress ranges. Now we need to find the probability of each stress range. Each stress range, how much is going to happen. We use Rayleigh distribution. This is a Rayleigh distribution. And we already know the RMS value. We can plug in for the 10 MPa stress range. What is the probability? It's 9%. For 20, it's a 21%, 24%. 2.4, right? Number of cycles, each stress range. What's the number of cycles each stress range? Now we have the probabilities. Let's find out how many cycles occur at each stress range. We know for the total number of cycles in 1 hour is 3600. So 0.25 seconds means it's going to be 14,000 cycles. Let's calculate the number of cycles at each stress range. So this stress range, for example, if I have this one, so 10 MPa, like this 1 2 3 4 5 6. So 10 MPa is coming, say 6 numbers. And if I take this one 20 MPa, like this one, this may be some 5 MPa. 5 MPa may come quite often, maybe 15 times. Like that we can see that particular stress range, how many cycles is going to happen, right? Out of in total, that particular stress range is how many times is going to happen. You got it, right? So this is the 10 MPa. 10 MPa, how many times it's happening. 5 MPa, how many times it's happening. And 2 MPa, how many times it's happening. Like that we can see probability of occurrence. Yeah. So the smaller one is going to happen quite often. Bigger one is going to happen a smaller value, that because it follows Rayleigh distribution. That's why we are getting this using this Rayleigh distribution. For example, 10 MPa, what is the probability is going to happen? So number of cycles is 14,000. Out of these 14,000 cycles, TZ, using TZ, and this is the probability of 9% and the 10 MPa, and the stress value is this one. So how many cycles is going to happen? So this is the probability. 9% is going to happen out of overall, right? And 20 MPa is going to happen 21%, 2.1%. This is 0.9, this is 2.1 percentage. This 10 is the stress range, right? That bin 10, it's a stress range. So we calculate the damage. So we can calculate the damage. So A equal to, this is 10 by 12 A, and this is the sigma power M. So we can get, so 1296 for 10 MPa, this actual number of cycles, and this is the allowable number of cycles, right? So we are getting this much damage. For 20 MPa, N by A by sigma naught power 4, right? Then this is the number of cycles to failure at 20 MPa. So damage is small n, then probability sigma value, all these values comes 20 power 4, that is sigma r power 4 m divided by a value is, a n value, that becomes 3.125. so this is damage. So total damage calculation, if you see, for each stress range 10 MPa to 100 MPa, 10 MPa 9% of probability, 2.1, 0.9, 2.1, 2.4, like that. We have different probabilities and number of cycles we can count, then total damage per cycle we can see it. So total damage, if you see it, 1.15, that means like 1 hour 0.125 it happens. So how much life does that mean? So now we have the damage value, remaining value we can see. If d equal to 1, component fails, right? So 1 divided by 0.15, 4.65 hours. So in 1 hour 21%, roughly 20, say suppose if it is 25%, 1 hour 25% damage happens, means in 4 hours is going to fail, right? And that's what it's 1 hour 0.215, and the remaining life is only 4.65 hours. So the structure will fail after 4.65 hours of this test stress under current conditions. Sensitivity, if you see, what if the RMS value is increased by 10%, how much more damage would that cause? If the sigma naught increases by 10%, sigma increases too. Sigma naught is the RMS value, and sigma r also is going to increase. That depends on sigma r per m, because damage depends on these stress range values. Increases by 10%, 1.464. That's almost 50% increase in damage. So small increase in RMS stress leads to much higher damage rate and shorter life. The whole process from the spectrum damage is like understanding the heartbeat of the material. Every wiggle, every cycle matters, and the whole process relies on the mathematical functions like Rayleigh, gamma, and to connect real world randomness to structural integrity. We can design a motor by understanding all these things, right? So fatigue is nothing but a story of thousands of tiny forces, each one small, but together they shape the fate of the material. Rayleigh tells us about the randomness, RMS about the strength of that force, Spectral wants about the rhythm and forces, SN tells us how these forces harm, gamma helps us sum it up all. Alright, time we have a new challenge. We need to find how much fatigue damage a metal pot gets when it faces a random loads like wave or wind. Fatigue damage, you mean when things break slowly because of many small pushes? Exactly, not one big hit, but many small hits again and again, like bending a paper clip back and forth until it snaps. That's it. And our goal is to find how fast the snapping happens mathematically. How fast that snapping happens, so how do we even start? We start with something called stress cycles. We start with something called stress cycles. Every time the stress goes up and down once, that's one cycle. So if the stress goes up and down and comes, that's one stress cycle. It can be quick or it can be slow. So every time it goes up and down, it comes back to 1. So that's one cycle. So how many cycles happen in 1 hour? So if you keep seeing that one in 1 hour time, how many cycles is that going to happen? So we call that number as n, number of cycles. Right, yeah, t is the total time. That's 1 hour. T is the average time between cycles. So this cycle takes 2 seconds, this cycle takes 3 seconds, this cycle takes 5 seconds. So average time between cycles, we can get it. So how do we find the tz? So we get it from the stress spectrum. So this is where, like, why do we get this tz? If we find out the tz, we can come to know how many cycles are happening, right, in 1 hour time. So in 1 hour, how many cycles are happening? So average time between cycles. So tz is average time between cycles. So each cycle, it takes different times. So to find out the how many number of cycles, we take the average time. So we get it from the stress spectrum. Two numbers called tz is the square root of m0 by m2. So m0 and m2 come from the graph or data. So they come from the stress spectrum, basically how much energy is in each frequency. So but the real stress is not the same at every time, right? So exactly, it's random. So we can't say every cycle has the same stress. We can't say that this cycle has the same stress and this cycle can be different stress. So we can't say that every cycle has the same stress. This is different stress, this is different stress, and this is also different stress. So each cycle has its own different stresses, right? And that's why we use Rayleigh distribution. It tells us how quickly each stress range is, how likely each stress range is. So for example, this small stress range might be more, and this stress also could be somewhat some percentage. This kind of higher stresses can be very low probability. So this probability is coming from the Rayleigh distribution. So we need to know the stress, how likely is that stress, right? How likely is that stress range? How likely is that stress range? So we can get it from the probability chart. The formula is, this is the probability, and sigma naught is the kind of average stress level. So with average stress level, once we know, then we can come to know that particular stress range. So once we know average stress level, we can come to know the probability of that some particular stress ranges. So small stresses are common, but the very big ones are rare. That makes sense. Like small waves happen all the time, but big waves are rare. So each cycle has some chance and some damage. How do we add it up all? So one small group of cycles with the stress between, this is the stress between these two, what's the group of cycles. So between this stress range, sigma to sigma, this stress, between these stress, how many cycles is going to have in that group of cycles, we can get this one. So that's the number of those cycles. So and the damage for those cycles, we use SN curve, which says how many cycles material can handle at a certain stress. At a certain stress, that means how many cycles it can handle. So higher stress means fewer cycles to break. So higher stress means fewer cycles to break. Higher stress means fewer cycles to break, right? The damage for that band is, this is the damage for that band. So to get the total damage, we add all small damages. To get the total damage, we add all small damages. Mathematically, that's an integral. So that looks scary. So don't worry, it's a standard integral. The result uses something called gamma function, which is like a fancy version of factorial. So it has a ready-made answer. Yes, that result is, this is like a gamma function using gamma function. So this is the final d that tells us how much damage the part gets in time t. For example, in 1 hour, how many damage is going to happen. That's how we can get it from that. If the damage is equal to 1, that means the full fatigue failure. So in short, we found how many cycles happen, how many cycles it happen. In 1 hour, how many damage is going to happen. That is the last one, adding above, for how likely each stress is and how much damage each cycle causes. So how many cycles happen, how likely each stress, that stress, how much damage is going to happen, how on that particular stress, how much stress, how much damage each cycle causes. The math gives us the neat formula with gamma function, so we can compute the damage without testing every cycle. So today we need to figure out how much fatigue damage the steel part will get in the ocean waves. You mean when something gets tired? Yeah, metals get tired too. Not sleepy tired, but cracked tired. Not sleepy tired, but cracked tired. Like when you keep bending a paper clip back and forth, it finally breaks, even though you never pulled it hard once, right? That's fatigue failure. Many small loads over time cause cracks. Many small loads over time cause cracks. So even if the waves are not strong enough to break it one go, they will slowly weaken it. So even if if it's not strong enough to break it in one go, they will slowly make it weaken. That's the danger. One big wave might not break it, but millions of small ones will. One big wave might not break it, but millions of small ones will. So first we need to know how many times the stress goes up and down. That's called the cycle. So we need to find out how many times the stress goes up and down. That's called the cycle. So one wave crest, one trough, right? Exactly, one full up and down is a one stress cycle. So if you know how many seconds one cycle takes, how long the sea lasts, we can find out how many cycles happen, right? If you know how many seconds one cycle takes, how many seconds it takes, say 2 seconds, and how long that sea state is going to happen. So it's going to happen, say 3600 seconds is going to happen. That means how many number of cycles is going to happen. 2 second one cycle means in 3600 second, how many cycles? So 3600 divided by 2. So this is the number of cycles. So we can get in the number of stress cycles. So we need to find out this tz, like tz is nothing but the average cross mean how many seconds it takes for one cycle. So we call that 10, right? So where t is the total time, say 3 hours. Tz is the average time period between cycles. In 3 hours, considering average time of 2 seconds, how many seconds is going to happen? So how long each wave swing takes. So if the wave comes faster, we have more cycles. If it comes very fast, quickly, then we have more cycles. Exactly, more cycles means more bending events, and more bending means more chance to get tired. So but waves are not small, are not same height, right? Waves are not all the same height. That's correct. Some are small, some are big. So stress in the metal also change randomly. Because the stress changes randomly, we use probability curve to describe how likely each stress range is. So stress is also not the same. So stress is going to vary randomly. So we use probability curve to describe how likely each stress range is. So this stress range is how likely it's going to happen, and this stress range is how likely it's going to happen. So like that, how likely this stress range is going to happen, how likely this stress range is going to happen. Right, and that we need to predict. So like saying small stresses happen a lot, big stresses are, the small stresses happen a lot. This is the probability, and this is the stress. So small stresses happen a lot, big stresses are rare. And the curve is called a Rayleigh distribution. Why Rayleigh? Because Lord Rayleigh studied the random waves and vibrations long ago. His formula works perfectly for random sea loads. The formula looks like this, and it looks scary. What's all that? It's just to say if the stress range is small, it happens more often. Stress range is small, if it happens more often. If it's big, it's rare. The exponential minus x squared part makes that the tail drop fast, meaning the giant stresses almost never happen. So sigma naught is likely the average size of stresses. Is the root mean square stress, kind of average power of that stress signal. Root mean square. Okay, now imagine we divide all those stress cycles into little groups, small ones, medium ones, and big ones, like sorting them into buckets. Each bucket has a cycles of certain range. Each bucket has cycles of certain range. The number comes from that small bucket. So this is the stress range, right? So for this stress range, this is the probability. So sigma PR for this one. This is the sigma PR. This is the stress. This is the bucket bin size. This is the probability of that bin size. And this is the number of cycles, overall number of cycles. So PR tells that fraction of that cycles in the bucket. Alright, so now the big question, how do we know how much damage one cycle causes? How do we know how much damage one cycle causes? That's where S and cause come in. It tells us how many cycles a material can survive at a given stress. So S means stress, N means number of cycles. The cause is N equal to A by square root of N A by sigma R power M. N becomes smaller if the stress is higher. If the stress is higher, N becomes smaller, meaning it breaks sooner. If the stress is higher, N becomes smaller, meaning it breaks quicker, sooner. So for a strong steel, A is large. A and N depend on the A and M depend on the material. M controls how sensitive it is to stress changes. If one stress level causes failure after N cycles, then one cycle causes damage of 1 by N. If one stress level causes failure after N cycles, then one cycle causes a damage of 1 by N. So the damage for all those cycles is 1. This makes sense. More cycles are higher stress means more damage. More cycles are higher stress. If cycles are more or stress is more, both are going to cause more damage. Now we just add up all those small pieces of damage from every bucket, from the smallest to the biggest stress. Adding up everything continuously is called integration. This looks complicated. Can we solve it? Actually solve it. It's known as a kind of integral mathematical forms. It's something called gamma function. Gamma is like it's not quite. It's just a function that helps solve problems where powers and exponential mix together. Here, if you see the powers and exponential mix together, after solving, we get this is the one. Gamma function comes where powers and exponentials mix together. It's like a factorials. So this final tells us how much total damage, fatigue damage and material gets in time t exactly if d equal to 1 the structure failures. Right, again, usually d is less than 1, this is okay like 20 hours. So the formula brings together everything: time, randomness, material strength, perfect summary. Can we go over what exactly simple really means physically? So Tz is the average period between stress peaks. How long one wave takes. N is the total number of cycles in time. How many times that part bends. Root means square. That is the average size of stress variation. Stress range. How big and up and down the stress swings. So SN constants. Gamma function math circuit for sum of all small damages to sum all small damage how tight the material is. So the whole process like counting all the waves and weighing how strong each one is. Counting all the waves and how strong each one, and adding the damages. So this one is going to cause some damage. So we have to see some waves may be high, some waves may be low. So each one is causing how much damage. So this is from our offshore structure. It lasted 8 years, but it was designed for 20 years. We need to find out why it cracked early. Did a huge wave hit? No. That's a point. Not a single big wave caused it. Then how did it break? Because of fatigue. You mean the metal got tired? Exactly. It didn't break once. It broke slowly. After millions of small stress edges. So the metal kind of remembers every stress it felt. Every second. Each tiny stress levels leaves a little scar. Over time those scars add up. So we can't ignore all small waves. All they matter. And our job is to measure how much the small damages those waves cost. Yesterday talked about the fatigue was great, but I'm still confused about the release thing. I kept thinking, why exact that formula? It looks so random. It's actually about randomness itself. The radial distribution comes from how peaks behave in a random signal. How peaks behave in a random signal? Imagine if the stress changes randomly, like a wiggle line. Most of the time it's small, and occasionally it spikes high, like a small C waves. Most of the day, and sometimes big one smacks the platform. So most of the time you are going to get the small values. These are the small values. These are the higher ones. The probability for getting the small ones is quite high, and probability for getting the higher ones, higher stress events, are quite low. The Rayleigh distribution describes how likely each stress range is in that randomness. But how does it really work? Let's write it down. So it's got a sigma, a square, and the we are x thing. X is just exponential. It makes the probability drop off fast for large stress ranges. That means like it starts from 0, it goes spikes, and then it goes like this. It's exponential. It drops off for the large stresses. These are the large stresses. This is the probability of that stress. These are the large stresses. It drops off for the large stress. Probability drop off fast for the large stress ranges. And the high stresses are possible, but very rare. The high stresses are possible, but it's very rare. Its probability is very less. The term exponential minus r squared by 4 sigma squared is the what makes the large stress events uncommon. Large stress events uncommon. What is that first part? What is that first part? Sigma r by 2 sigma naught squared. That's what makes the curve rises at first. That's what makes the curve rises at, because there are many ways small stresses can appear. It goes up, reaches a peak, then falls. So it's like a hill. Small stresses are common, medium ones are most likely, huge ones are rare. That sounds like a real C. What's the link with probability? What's the link with probability? Probability density function. P of R is the probability's density function. If you take a small range of stress, sigma r plus dr, if you take this as a dr, that means this one. If you take a small stress range from this one, P of r into dr tells you what fraction of cycles fall there. This is a fraction. This is a fraction probability. So if you integrate the P of r over all possible stresses, if you integrate completely, you are going to get the complete area. So probability is 100%. That's the total probability, all cycles together. Okay, now what about this sigma naught? It appears everywhere. Sigma is the root mean square of the stress. RMS, root mean square, that sounds like, it means take all the stress values, square them, find the average, then take the square root. It's like you are having the stress values, right? Take all the ones and then square them and find the average, then take the square root. Why square them? Because some stresses are positive, some stresses are negative, both cause fatigue. So squaring removes the sign, so mean measure the total effect. It's like saying we don't care if the wave pushes or pulls, both matter equally. The root mean square value tells us the average energy of the stress fluctuations. So sigma naught tells us how strong the stress usually is. The Rayleigh curve tells how it varies around that. So sigma naught tells how strong the stress usually is, and Rayleigh tells us how it varies around that. So if you keep saying stress range, is that the difference between the highest and lowest stress? Stress range, sigma is the stress range. That's the difference between the highest stress and lowest stress. If the stress goes from plus 30 to minus 10 in one cycle, for example, this goes plus 30 and comes down minus 10. This is the plus 30, this is the minus 10 in one cycle. So stress range is, this is the stress range is 40 MPa. What about amplitude? Amplitude is the half of that range. So but in fatigue we usually use a range because it fully describes the swing from peak to trough. So in relay world we are talking about how those stress ranges vary randomly. So we are talking about the stress ranges, and that's what PR gives us, the probability of seeing each stress range. I still don't fully get those spectral moments, M0 and M2. Let's dig into that. Imagine the stress signal as a song full of different frequencies. Some are slow, some are fast. The stress spectrum tells us how much energy is present in each frequency. Mathematically, ith spectral moment. This is a power spectral density, how much stress power at that frequency. M is like a total area. So M0 is the variance of the stress signal, the average of the square. So M2 is that one weight, the energy by frequency squared. So it tells us how fast the signal changes. M2 cares more about how the high frequency is equals. That's why average time it peaks related to M0 by M0. If M0 is large, the signal changes fast. Shorter periods between cycles. That's how we found T is equal square root of M0 by M2. It's like dividing the total energy by how fast energy moves. So now the gamma function we use is ready. What is that thing? It's kind of it's defined as this some power term and exponential term. But what does it mean? It helps us handle the integrals that have powers and exponentials together. In integrals, if you have powers and exponentials together, why not just calculate normally? Because same kind of integral appears everywhere in fatigue, probability, heat, even quantum mechanics, so mathematics give it name. Gamma is like universal shortcut for this kind of integrals. Exactly, it also connects to factorials. Gamma n is nothing but n minus 1 factorial. So when we got gamma 1 by m2 in the fatigue formula, it just came from integrating over all possible stress range. Mathematical summary of how all these probabilities combine. Gamma handles the heavy math while we just care about the result. It gives us the total combined effect of all possible stress ranges on damage. So damage is nothing but basically number of cycles, average stress effect, and the mathematical combination of probabilities. So probabilities, average stress effect, and number of cycles. Can relay ever be wrong? Can the relay ever be wrong? Yes. If the stress process is not narrow band or Gaussian, in that case we use corrections. Count actual peaks from the time history, that's called rainflow counting. Relay is like an approximation works best when the stress are random but smooth. The ocean is pretty good for narrow band waves. The machines like turbines engines, we would often need time series counting instead. But then this approach gives a great insight. How that every term now makes sense physically.